Hi class, welcome back to our next video. This is section 3.6. Today we're going to talk about rational functions. So rational functions are pretty much whenever you have one function over another function. Today we're going to really just focus on when both of those functions are polynomials and how to graph those. Right? So this makes up a big part of algebra and calculus. So we're really going to use all the methods we've learned so far in this course to analyze these graphs, right? These functions and their graphs together, really. So today we're going to explore how these graphs behave, how these functions behave, and how to graph these functions. So there's a couple of cases that we have to take into consideration. So again, we are going to use some analytical methods by looking at their functions in order to get an idea, okay? So again, we're looking at rational functions, right? Fractions, basically, where the numerator and denominator are both polynomial. So we have a function f of x that's made up of a polynomial p divided by a polynomial q. Okay, so the main thing for us to focus on in this section is very similar to the things we had to focus on in the polynomial section when we're talking about graphing polynomial. So remember, when we were graphing polynomials, we were interested in the zeros of the polynomial, and then we were interested in the y-intercept. And then we were interested in the multiplicities of the zeros because that kind of told us what the polynomial was doing. So here we're interested in some of the same stuff. Oh, and we were interested in the end behavior. Okay, so here we're interested in a lot of the same thing. We want to know the zeros. We really want to know the zeros of the numerator and the denominator because they both tell us different things. The numerator tells us the actual zeros. Remember, you can never have a fraction with 0 on the bottom. So we want to know the values that we're not allowed to plug in. Okay, those give us those what are called the vertical asymptotes. So we want to know the zeros of the numerator, the zeros of the denominator. We want to know what the end behavior of our function is in general. And that's pretty much it. And our y-intercept. That's also important for us. So that's what we're going to be looking at. The zeros of the numerator polynomial, the zeros of the denominator polynomial, when x equals 0, because that's my y-intercept. And then we also want to know what the degree of p of x is and the degree of q of x. So this tells me my zeros. This tells me my vertical asymptotes. This tells me the y-intercept. And these two together help me to understand what the end behavior of my graph is. So 4 and 5 work together for us. All right, so again, just to reiterate, the zeros of p of x, the numerator, are going to be the x-intercept. They actually tell us where the holes of the graph are if they share a 0 with q of x. So if p and q both have a 0 at the same location, it's no longer a 0 or a y-intercept. It's kind of a, no, it's not a vertical asymptote. It'll be a hole in the graph, okay? The zeros of q are the vertical asymptotes, so they're like invisible fences that we're not allowed to cross. And then the relationship of p and q, the degree between them, right, determines what the horizontal asymptote and what the end behavior of the function is overall. Okay, so let's talk about end behavior first because it's the one that has the most cases, and once you understand the end behavior, then we just focus on what's happening in the middle, right? So again, the middle is the y-intercept, the x-intercepts, the vertical asymptotes. Okay, so once we know what happens at the end, then we can focus what happens in the middle because the middle is kind of what shapes our graph the most, right? So we're going to use a lot of that limit notation here. So hopefully you guys are familiar with that and you've been reviewing what we have previously. Okay, so let's say that p is a polynomial that in this case has a's and n's, and q is a polynomial with b's and m's, right? So all of this is saying is that p is a polynomial, q is a polynomial, and we're trying to distinguish between the two when we talk about them, because if we said that q looks exactly like p, we'd be very confused. So for p, we're using coefficients of a and powers of n. Q is coefficients of b and powers of m, right? So the indices are m's and the indices for p is n's. Okay, so if n minus m is a negative integer, right? Z negative is negative integers. So let's just think about this notation before we even begin, right? N minus m is a negative integer, okay? P is on top, Q is on bottom. If n minus m is a negative value, right? So if the degree of P has to be less than the degree of Q in order for me to subtract them and have a negative number out, right? If it's the top minus the bottom and I get a negative number out, that means Q is a larger number, okay? So if that's true, what we say then is that Q dominates the function. So as I plug in very large values of X, Q is the one that has the most input into the function, right? Because Q grows way faster than P does because Q has a higher degree, right? So this would be like X squared over X to the 10th, right? The X to the 10th grows way faster on the bottom than the X squared does on top, right? So in this case, the Q function is a function that dominates. So we talked about this back in chapter 1, so I know we're talking a lot before we get into what this looks like. But remember what happens when we plug in very large numbers in a denominator, okay? 1 over 1 is 1, right? 1 over half is less than that, right? A 2 on the bottom gives you a smaller amount than when there's a 1 on the bottom. 1 over 100 is 1/100th. That's small. If I plug a million in to my denominator, I have 1 over a million, or 1/1,000,000th, a very, very small amount. So the larger the denominator is, the smaller the actual value is. The closer and closer and closer I get to 0, okay? So if my bottom function dominates the top because the degree is larger, then as I plug in very, very large negative numbers or very, very large positive numbers, I will get out values that are very, very close to 0, right? If I plug in a billion, it's basically 1 over a billion. That's a very small number. It's very close to 0. Same thing if I plug in a negative billion. 1 over a negative billion is a very, very small value, very close to 0. So if my bottom number dominates because it has a higher degree, then my limit, my end behavior is that on both ends, both extremes, as I go to positive infinity or as I go to negative infinity, my function gets closer and closer to the 0 axis, right? Very much so like an exponential function. When you go very, very large out and you just kind of decrease towards the x-axis. That's what happens, okay? N minus m is a negative integer, right? Meaning that smaller power on top, larger power on bottom. You subtract those, you get a negative value. Basically, the denominator dominates, okay? Now, if n minus m is 0, that means that p and q are the same degree polynomial. Neither of them dominates, okay? And if neither of them dominates, then that means they're basically canceling each other out for the most part, right? So as I plug in very, very large values of x, right? If this is x to the n, let's say this was x squared and this was x squared, well, the x squares basically cancel because those are the things that dominate the function. All the other stuff doesn't matter, right? Now when I plug in very large values. So when I plug in very large values, the lead powers, right, the dominating powers basically cancel and I'm left with a over b. So if neither of the polynomials dominate, right, meaning neither of them have a larger degree than the other, then the limit as I go in the negative direction forever, right, very large negative values or very large positive values, is just the ratio between a and b, okay, the lead coefficients. Now, if I subtract the two powers and I get a positive integer, that means that my p function has a higher degree, right? If the p function has a higher degree, then that means that p is going to dominate, right? And in that case, if p is going to dominate, then my limit as I go to infinity or negative infinity is basically going to act like a polynomial of degree n minus m, right? So again, if my degree of my numerator, right, is higher than the degree of my denominator, then when I go to very large negative values or very large positive values as inputs, my function behaves the same as a polynomial would that has a degree of whatever n minus m is, okay? So again, if the ratio between A and B are positive, okay, so meaning that neither of these has a negative value in them, then it's going to go to infinity, okay? And that's only if it's even, because what do even polynomials do? They act like u's, right? So as I go to negative infinity or positive infinity, my outputs will go towards infinity, right? So if n minus m is even, but this is negative, it's going to act like a negative valued even degree polynomial, because n minus m is like a square or a quadric, right? Or a sextic, or whatever that is, an even degree polynomial. So again, if the ratio between the lead coefficients is negative, it'll be like an upside down u, right? So as I go to negative infinity and to positive infinity, I'll get out negative infinity. It'll be like a negative u, right? If those are odd, same thing, right? The lead, the numerator dominates. If the difference between them is odd, okay, and this is in positive value, then it's going to act like a linear function. It's going to go negative, and then as I go to the right, it's going to go positive, right? So as I go in the negative direction, it'll be negative infinity, and as I go to the positive direction, it'll be positive infinity. And the last case is, again, that the numerator dominates the function, and that when I subtract the two powers, that I'm getting out an odd value, so my function overall acts like an odd degree polynomial, okay? And if I happen to have the ratio between the two lead coefficients being negative, then this just switches, right? As I go in the negative direction, it'll be positive, and as I go in the positive direction, it'll go negative. So it'll be basically decreasing overall, right? Okay, so that's the way that it works. So these two go together, the middle two go together, and then the first two are two separate cases. Okay, so again, this is the denominator dominates the function. This is that they both cancel each other out, basically, right? Neither of them dominates. And then these four are what happens when the numerator dominates. Okay, the first two are saying that the numerator is dominating, and it's acting like an even polynomial, one with the positive case and one with the negative case. And then the last two say that the numerator is dominating the function and that it is acting like an odd polynomial based on the difference in the powers. And so we have one where it's acting like the normal case, decreasing overall or increasing overall, right? Starting from the negative direction heading to positive. And then this is that it is starting in the positive direction and heading towards negative. So overall, it's decreasing. Okay. So now let's talk about asymptotes, right? It might take a minute for you to digest this. We're going to look at a bunch of examples. So don't worry about that. Okay. Let's look at asymptotes, right? So there's three different asymptotes we have to worry about. There's vertical asymptotes, horizontal asymptotes, and slant asymptotes. We talking about end behavior, we already talk about the horizontal asymptotes. So here we have horizontal asymptotes of 0, of an over bn, or there are none horizontal asymptotes. So the case where the numerator dominates, there are no horizontal asymptotes. We don't have to worry about that. If they both cancel each other out, then the horizontal asymptote is the ratio of the lead coefficients. If the bottom polynomial dominates the function because it's a higher degree, then the horizontal asymptote is 0 because both sides tend to go to 0. So that's the horizontal. For the vertical asymptotes, we're just looking at the zeros of the bottom polynomial, right? So these are values that our function can approach and get as close to as it needs to, but it can't touch the value and it cannot pass through the value, okay? So that's what a vertical asymptote is. F of x approaches the vertical asymptotes from the left of our function and from the right side of our function. Okay, so we see that f of x has a vertical asymptote at x equals k if k is a0 for q of x. Okay, so at that asymptote, we have to talk about what happens as we come from the negative side towards k from the left And what happens as we come from the positive side towards k, or from the right? So we say from the left is from the negative side, because at the line x equals k, which is a vertical line, the negative values are to the left of that line. So as we come from the negatives towards the positives from the left, we have to talk about what our function is doing, right? Our function is either going to grow towards infinity or it's going to grow towards negative infinity, okay? Because it cannot reach a value at k, right? K is a vertical asymptote. It's a wall. I can get close to it, but I can't touch it. So as I can only go to infinity or towards negative infinity at a vertical asymptote, right? So our notation for that is the limit of f of x as x approaches k from the negative side, right? Or from the left. And again, that's either going to equal a positive infinity or a negative infinity, right? Not plus or minus infinity. There's two different cases, so we have to consider both cases, right? So this is only for vertical asymptotes. When we get to calculus, we'll talk about this some more, but it can be an actual value here because k most likely will not be an asymptote when we're talking about it in the calculus sense, right? But for right now, k is a vertical asymptote. As x gets closer and closer to k from the negative side, from the left, we're either going to go to positive infinity or to negative infinity. Okay, and as we come from the other side, from the right, and again we call it from the positive side because at that vertical asymptote, all the values to the right are where the positives are. Now there could be negatives as well, but the positive values lie on the right of that line, no matter where that line is at. Okay. Same thing as we approach that vertical asymptote, right? K from the right side, from the positive side, we're either going to go to positive infinity or towards negative infinity. So the notation here is slightly different. K plus means we're coming from the positive direction. Here means we're coming from the negative direction, where the negatives are, right? So here we come from the left towards k. Here we come from the right towards k. Okay? So the only time we have to talk about slant asymptotes is when the difference between n and m is 1, right? So the numerator polynomial is 1 degree higher than the polynomial on bottom. When that's true, we have to use polynomial division, right? So depending on what the powers are, we may be able to use synthetic division, or we might have to use long division, right? It really just depends, because remember, we can only do synthetic division when we're talking about dividing by a linear factor, right? So if the numerator is a cubic, a polynomial of 3 with a degree of 3, and the denominator is a polynomial of degree 2, a quadratic, well, we can't use synthetic division. We have to use long division in order to figure out what the slant asymptote is at that point, okay? So again, it's slanted. So the equation for the slant asymptote is the linear quotient when we divide these two polynomials by each other, right? If n minus m is larger than 1, then we have an asymptote in the shape of the resulting polynomial for the quotient when we're dividing p of x and q of x, but we don't really have to worry about that. That's not going to pop up too often. Really, we just have to worry about a difference of 1. That's the one we're going to come across a lot, but it's very possible that we have a quadratic asymptote. So it takes the shape of a quadratic. We're going to do some examples, but I'll look at even more examples on Desmos towards the very, very end of this video, so we can play around a little bit faster than we normally do, okay? Again, if the numerator and denominator have a shared 0, okay, then that 0 is a whole, okay? We call it a whole. So to finish forming a full graph, we take a few key points, just like we do with polynomials, so that we can have a good idea of what's going on in between the zeros and the asymptotes and the wholes and all those other things that we know, okay? So now we have enough information to graph all of our stuff together. So we're actually going to do 3 examples because remember what we have here. Here we actually, even though it looks like 6 cases, there's only 3. There's one where the denominator dominates the function. There's another case, and behavior-wise, where neither the numerator or denominator dominates. And then we have the case is when the numerator dominates, and then how to break that down. Okay, but here is easy because these 4 cases you should be familiar with from when we're doing polynomials. Okay, so we'll have one example for each of these 3, right? So this is 1, this is 2, and these last 4 are really all from the same sort of case. Okay, so let's go ahead and start with our first example. So here, it'd be nice to know what is my case, right? Well, it looks like the denominator has a higher power than the numerator, so the denominator is going to dominate the function, right? When I plug in very, very large values, it's the denominator that grows faster than the numerator. So this will act like 1 over x, or 1 over x squared, or 1 over x to the 10th, or however, right? So as I plug in very large values, this becomes very large faster than this does. So this is that first case that we're looking at, right? Okay, so remember that the first thing that we really want to do is find the zeros of the numerator and the zeros of the denominator. So the easiest way to do that, just factor everything, right? So if I factor everything, it's very easy for me to find the zeros. So number 1, I'm going to factor everything, okay? So the numerator factors 2 times x plus 2. The denominator factors 2x plus 1 times x minus 3, right? So from here, I can find my zeros and my vertical asymptotes. Again, the zeros are what makes the numerator 0. The vertical asymptotes are what makes the denominator 0. So the only x-intercept is x equals -2. The vertical asymptotes are x equals -1 and 3. Okay, -1, 3. The y-intercept is what you get out when you plug in 0 everywhere. So we can look at this or at this. Either way, it doesn't matter, but 0, 0, 0. I'm left with a 4 and a -3, right? So when I plug in 0, I get out -4/3. So that is my y-intercept, okay? Now my end behavior, here, the difference in degree is a -1, okay? So that means, again, that the denominator dominates. So as I plug in very, very large numbers, I get very large numbers on the bottom, which means overall my function is very close to 0, right? When I plug in very large positive numbers, my function overall is very, very small, right? 1 over a million is a very, very small number, very close to 0. So as I plug in bigger and bigger numbers, I get closer and closer to the x-axis, right? So that's my end behavior. So I can do that either by analyzing which function dominates, and just looking at the function overall, or looking at it as a case-by-case thing, right? N minus m is -1, and then going, okay, what case is that? And looking at this little table, which, I mean, look at this thing, it's crazy, right? Well, that is n minus m is a negative integer. So that's case 1. So -infinity, infinity, 0. So that's what I would get out. Okay, so I can look at this, or obviously an easier way is by analyzing the function and seeing what happens when we plug in large values, right? Which function dominates, numerator or denominator, and then how. 5 is looking at additional points, okay? So when we say additional points, the additional points we really want to check are values that will let me know what's happening near my vertical asymptotes, okay? So I have an x-intercept. That's the only time my function crosses, and as you can see, this intercept is has a multiplicity that's odd, so it crosses at x equals -2. It doesn't bounce off the axes, right? It crosses because it's an odd multiplicity, so that's nice to know. So I would like to know what happens around my vertical asymptotes, okay? Because if I only cross axes once, I need to look at values that are to the left of -1, then in between -1 and 3, and also above 3. And I don't have to find the actual values, I just need to find the signs. Because if my function is positive, right, on one of the sides of my asymptote, then it will always be positive, and it will go to infinity as it approaches my asymptote, right? Especially since it never crosses the axes. Because if it's already positive, then as it approaches my asymptote, either from the left or from the right, it will stay positive because I know it never crosses my x-axis anywhere else. So if it's positive, it'll stay positive. If it's negative, it'll stay negative. So that allows me to understand the behavior of my function near my asymptotes. So we need to check for the signs near my asymptotes. So the nice thing about that is I don't have to actually calculate values. I just have to figure out what the signs are going to be. Okay. So again, we don't know what the graph is doing near my vertical asymptotes. So we're going to check on either side of those. So I have to check somewhere on the right, on the left of -1 to the right of -1, but less than 3, and something to the right of 3, right? So a value in between each of those. So my asymptotes are the values in the middle. Okay. So we really, again, just need to check if it's positive or negative, especially since I know it doesn't cross the x-axis. Okay. So here I'm going to start off with -1.5 because -1.5 is in between my 0 and my asymptote. So checking between those two values, if it's negative, well, it's not going to cross again because it's only crossed at this one point, right? Now, if it's negative, it's going to stay negative as it approaches -1, right? If I chose a value that was too far out, like -3, okay, and I get that -3 is positive, well, I know it's going to cross my x-axis at -2 as it's getting closer to 0, right? And so then that means it will have to stay negative as it approaches -1, and it'll go to -infinity. So I can figure it out that way, but it's just easier to find values in between the 0 and the vertical asymptote, because whatever that sign is, that's what I'm going to approach. It'll tell me that I'm going to stay either positive infinity or negative infinity. Okay. So using -1/2, I am going to plug it into the factored form, right? So for -1/2 plus 2, well, -1.5 is less than 2, right? Absolute value wise. The 2 will dominate here. It's going to stay positive on top, right? -1.5 is more than 1, so this will be negative. And here I have a negative minus another negative, so this will be negative. So on top, I'll have positive and a negative times a negative. Okay, positive and a negative times a negative. So again, I just need to understand what the sign is going to be. I didn't have to calculate any actual values, just which is larger. Do I have more positives or more negatives? So overall, it'll be positive on top, right? Over here, I had more negatives than positives, so overall, it's negative. Here, I had 2 negatives, so it's negative still. Now let's look at the relationship. Negative times negative is positive. So this is really a positive over a positive. So in between my 0 and my vertical asymptote, I'm getting a positive value out. And I know it's never going to cross my axis again after -2, right? So I'm in between -2 and -1 at -1.5, and I'm positive. It'll always be positive, right? So -2 was a 0. So therefore, as I get closer to -1, my function is becoming larger and larger, right? It's staying positive. So it'll stay positive. It will never cross the x-axis again after -2. So I know it has to stay positive, and I can't have an actual value at -1, so it stays positive. So the limit of my function as x goes towards -infinity from the left side, from the negative side, is a positive infinity. Okay, I'm going to do that with another one. So the next value that I would check, some value in between -1 and 3. Here I chose -1/2 because I already know what happens at 0. So I'm choosing a value in between -1/2 and 0. However, I know 0 is negative. My function never crosses the axis again, so it stays negative, right? But here I'm actually checking the values again. Positive over a negative is a negative. So my function is negative as I approach -1 from the positive side. Okay. So if it's staying negative and I never cross the x-axis again, well, I know that's true for as I approach 3 from the negative side, because again, there's no zeros in between -1 and 3, the two vertical asymptotes. So there's no way it can start to go positive towards positive infinity if all I have is negative values there, right? So it has to go to -infinity. So now I need a value on the other side of 3, right? So I can talk about what happens as I approach 3 from the positive side. So when I plug in 4, remember this was x plus 2 on top, so a positive and a positive, right? This was x plus 1, so positive plus a positive. And then here was x minus 3. Well, 4 is more than 3, so it's all positive, okay? So therefore, as I approach 3 from the positive side, I go to positive infinity, right? So now we have enough to put it all together, okay? So hopefully you guys are taking notes here, and let's talk about what happens. All right, so we can start with our one known value, which is the x-intercept. We also know the y-intercept, which is -4/3 or -1 1/3. Okay. We know what the vertical asymptotes are, right? X equals -1 and x equals 3. So these are lines we are not allowed to cross or touch. Okay. I know that in between -2 and -1 that I have positive values, right? So if I checked right in the middle, it was a positive value. Since it was a positive value, it's going to stay positive value. So as it gets closer and closer to 1, it doesn't just get close and stop. It goes up and it gets as close to -1 as I can, but it never reaches it. It just keeps going up and up and up and up and up and up. Okay. I also know that it crosses the axes, right? So here's positive. So I know it crosses the axes because x equals -2 was a 0 of multiplicity 1, right? An odd multiplicity. And I know that I get close to 0 as I go in the negative direction, and I get close to 0 output-wise as I go in the positive direction. So I know what the end behavior is. So this one has to be negative and very close to 0. And then as it comes here, it has to cross the axes at x equals -2, and then just get more and more and more positive because it stays positive as I get close to x equals -1. Just like that. Okay. Here, I know that I have a negative value out. I also checked the value of -1/2 and it was still negative. Okay. And I know that then it has to get close to -infinity because it can't touch this line, but I can get very, very close, right? And as I go this way, it has to do the same thing. It has to get very close to x -3. It has to go towards -infinity because it never crosses this axis. So it can never go up, right? Because this is the only 0. So here it should be somewhat of a U shape. Okay? So the limit as I approach x equals -1 from the right, from the positive direction, that's why it puts a little plus because the positives are on this side of this line, I reached -infinity, right? And as I approached -1 from the left, from the negative side where the negatives are, I approached positive infinity. As I approached 3 from the left where the negatives are, I approached -infinity. Okay. Boom, boom, boom. Okay. Again, the limit as I approached -1 from the left was positive infinity. As I approached -1 from the positive was -infinity. As I approached 3 from the negative from the left was -infinity. And as I approached 3 from the positive side was positive infinity. Oops. Okay. So same thing. I know that I go towards 0 as I go to very large values. And as I approach 3 from the right, I go towards very large values, right? So end behavior is that it goes towards 0 the further I go. And then I have my behavior on the left side of my vertical asymptote, the right side of my vertical asymptote, the left side of my vertical asymptote, and the right side of my vertical asymptote. The positive side, negative side. For this one, it's the negative side. This would be the positive side. Okay, that's how we put it all together. So that's how we look at limits at infinity, limits at a point, right? From the left side and the right side, from the negative side and the positive side. So we got 2 more examples. So let's go ahead and work through them. We're going to do the exact same thing. We're going to start with our function. We're going to factor everything. Okay. The zeros of the numerator are the 0 values that I have for my x-axis. The zeros of the denominator are my vertical asymptotes. I look at the end behavior. In this case, notice that neither of these functions dominate. They both are cubics. Okay. And then I look at my vertical asymptotes and I talk about what happens on the left of them and the right of them based on the zeros. Okay, so I always look in between the zeros and the asymptotes, which we'll see here. Okay, so here, same thing. We're going to factor everything. Okay, so to factor this, we can try to do a factor by grouping, because as you see, we have the same coefficient twice. So that'd probably be the easiest, right? Pull out the 2. Here we can, again, factor by grouping. So we can pull out an x squared here. We can pull out a 4 here. Notice we have the same binomial common factor, so we can pull that out. So we have x squared minus 4. We have the common x plus 1 term that we factored out of both of the x squared and the minus 4 terms. And then this is x plus 2, x minus 2. So we actually have 3 zeros. They all have multiplicity 1. So the graph crosses at x is -2, -1, and +2. Okay. So for the denominator, looks like we can do pretty much the same thing. Okay, we can factor out here an x squared term. Here we can factor out a -1 so that the signs match for the binomial terms. Again, we can use synthetic division here like we've been using, but if we have other methods that work that are a little faster, we can go with those. So I have x squared minus 1, x minus 1. So here we have x plus 1 and x minus 1 squared. We don't have to worry about the multiplicity because this is in the denominator. It has nothing to do with the zeros of the function. It just has to do with the vertical asymptotes. Okay, so the multiplicity on the denominator does not matter at all. So when we factor everything, it looks like this. Okay, so if you notice, we have one point where we have a common 0 in the numerator and denominator. That doesn't mean we cancel it out, okay? But it does mean that we have a hole in our graph, right? Because there's a common 0 in the numerator and in the denominator. So we'll talk about that later. But for right now, let's use this factorization to talk about my zeros and my vertical asymptotes, right? So I have a hole at x equals -1. So x equals -1 is not an asymptote. Okay, I'm going to be very clear here. It is not an asymptote because it's just shared 0. So that takes it out of the vertical asymptote category and it turns it into the hole category. So it is not the same as a vertical asymptote. Right? My x-intercepts are the zeros in the numerator. Okay, and again, that is just these values because this is a hole. It is no longer a 0. Okay, so that brings it to -2 and 2. Again, a hole takes you out of the 0 category and out of the vertical asymptotes category. Okay, so my vertical asymptotes then are just this one shared one, right? So x equals 1. Okay, so this is a hole because it's a shared 0. These are the remaining zeros in the numerator and remaining 0 for the denominator. So that's my hole, x-intercept, and vertical asymptote. Okay, my y-intercept is what happens when I plug in 0. It's easier to just look at this because it's whatever doesn't have an x, right? So -8 and 1. So therefore, when I plug in 0, I will get out -8. So that's where I know where it crosses the y-intercept, right? So the next thing that we have to do, so this is always the easy stuff, okay? Next is checking for the positives and negatives between my vertical asymptotes, okay? My vertical asymptote. I want to know what happens as I approach x from the left and from the right. The nice thing here is there's only one. I only have to look on one side of both, right? One side of from on the left side and on the right side. Now I have zeros and I know that they cross here. So I want to look at values that are in between -2 and 1 and a value that's in between 2 and 1. So the nice thing is I already have a value between -2 and 1, 0. So I already actually know already. So when I plugged in 0, I get a -8. So I know that as I approach 1 from the negative side, right, it's going to stay negative because in between -2 and 1 as x's, I have x equals 0. I got a negative out. It never crosses the axes again. I don't have to worry about it, right? So I know that as I approach this from the left, it'll be negative. So now I'm going to plug in a value in between 1 and 2 to know what happens when I approach from the right. So the easiest one would be 1.5, right? So end behavior. I know what the end behavior is. They cancel each other out. So as I go to negative infinity or positive infinity, it's the ratio of the coefficients. There's no negatives here. So that's just the value of 2, right? So as I go to negative infinity, I'll approach 2, okay? And as I approach positive infinity, I'll also approach 2, right? So 2 is my horizontal asymptote. So for the limits at the vertical asymptotes, remember the only value the only vertical asymptote I have is x equals 1. One of my zeros is -2, but I have a value in between my 0 and my asymptote already, okay? So again, this is my vertical asymptote. I have my first 0. The value in between that at x equals 0 is -8. It never crosses the x-axis again from -2 until I reach 2. So if I'm negative between x equals -2 and x equals 1, I stay negative, okay? So the nice thing about that is I already have a point, right? X equals 0 is between my 0, x equals -2, and my vertical asymptote. So the graph stays negative and it never crosses the x-axis again. So therefore, as I approach my value of 1 from the left, from the negative side, right, I go to negative infinity because I already have negatives, okay? So I actually really only have to check one value. A value that is in between 1 and 2, so 1.5 works, okay? And we already kind of walked through this a little bit, right? So 1.5 minus 2, well, 1.5 is less than 2, so this will be negative. Positive plus a positive, positive plus a positive, positive plus a positive. 1.5 minus 1, well, 1.5 is more than 1, so this will stay positive. Even if this was negative, it would end up getting squared and be positive anyways. So I have plus, 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 and 1 negative on top, okay? So here, overall, I'll be negative, right? So as I approach 1 from the other direction, I will be negative, okay? And then I'll hit at x equals 2, and I'll go into the positive side of things, okay? I know that also because, well, I tend to get closer and closer to y equals 2 as I plug in larger and larger values for x. So I have to cross over if I'm negative, if I'm going towards negative as I approach 1 from the right, right? Because as I go x very large, I go to the positives, and that makes sense because I have to cross at x equals 2. So plug in my zeros, okay? One is at x is -2, the other is at 2. I have a vertical asymptote at x equals 1. Oop, I'm sorry. Let's do my y-intercept at -8, and x equals 1 is my horizontal, my vertical asymptote. So as I know, as I go very, very negative, I approach the value -2, or positive 2, right? So this line is what I get close to as I go to infinity, negative infinity, and positive infinity. So I'm going to start somewhere over here. I will cross and start to become negative because my end behavior, right, or my behavior near my asymptote. So as I approach 1 from the negative, I go to negative. So I'm going to be positive. I'll cross, and I will cross here, and I'll continue to get negative, right? That's my first value. And as you can see here, I have my hole in my graph because x equals -1 was a 0 for the numerator and the denominator. So it's not a vertical asymptote, and it's not a 0. It's literally just an open point along my line. I am not evaluated at this point. I can't plug in x equals -1 into my function. So it's a hole there, right? Next, I know that as I approach 1 from the positive side, this way, I have negative values. So in between my 1 and my 2, all my values are negative, right? So I have to come from here. I'll cross at 2, and I will approach x equals 2. Okay? Now, you might be saying, well, Professor Williams, 2 is my end behavior. That's a horizontal asymptote. You can't cross. Yeah, actually you can. Vertical asymptotes, you can't. Horizontal asymptotes, you're allowed to cross. I can cross the line x equals 2. It's just that as I continue on to infinity, I have to get closer and closer and closer to that value as time goes on. Same thing here. I'm going to approach from the bottom. Here, I actually approach from the top, right? I'm coming down towards 2. Here, I'm getting larger and larger towards 2. Okay? And really, the only way to figure out which one is which is by plugging in a couple of extra points, right? So that's the graph of my other function. Okay, so that was, again, you can see y equals 2. That's that horizontal asymptote. Both sides get close to that. I have my vertical asymptote, my zeros, my whole, my y-axis, right? So I got one more example, okay? And again, if we talk about the horizontal asymptote, this is just repeating that the horizontal asymptote can be crossed, the vertical cannot. Neither can a slant asymptote or any kind of polynomial asymptote. The function achieves a value of 2 at some point, but as I go towards negative infinity or towards infinity, my function tends to settle towards a value of y equals 2. A nice additional point to have had when graphing this would have been, when am I actually equal to 2? Because then I know, well, hey, if I know that I was 2 at somewhere between 2 and 3, well, I know that that's the only time I have that value, and I will actually, I'd have to cross it and then settle towards it as I continue. If I'm never 2 on the negative side, well, then that means I'm coming up towards it, right? But if I have it equal to 2 on the left or on the right side, that means I hit that value, I go above it at some point, and then I settle down towards it, right? So that's how I know if I'm coming up towards it or settling down towards it. And the easy way to do that is to just set 2 equal to my function, right? So 2 equals this. I can divide everything by 2 because remember, in my numerator, everything was a factor of 2. So I can then clear out this denominator and multiply both sides by x cubed minus x squared minus x plus 1. And basically what that does is it allows me to set these two polynomials equal to each other at that point, right? So I have x cubed minus x squared minus x plus 1 on one side, and the numerator stays on the other side. So I basically cleared my denominators out. Here, easiest thing to do is to set it equal to 0. So x cubed minus x cubed, add this over. So I got 2x cubed. Add this over, you have minus 3x, and then subtract this over, you got minus 5. This is actually factorable, which is nice, and we get x plus 1 and 2x minus 5. Okay. However, we know that x plus 1 is one of the zeros that we had, right? X minus 1. That was actually where our whole was at. So this is an extraneous answer because I can't even plug this into my function. But that tells me that a positive 5/2, right, or 2.5 is where I'm equal to 2. Okay, so again, extraneous solution because I can't plug in -1 to this at all. But the other 0 at in between 2 and 3, 2.5, that's where I have the output of 2. Okay, so I don't worry about the other solution, that one of x plus 1, because the 0 here, the value that makes the 0 that works for this equation, I can't even plug it into my equation to say it equals 2, because if I plug in -1 on top, that goes to 0. If I plug -1 on bottom, that gives me an undetermined answer, right? Undefined. So this gives me a value that solves this that I can't even use here, right? So this is the only value that works. So x equals -1, it's a whole. So the only time our function is actually equal to 2 is at the 0 for this, which is at 5/2 or 2.5, right? So let's do our last example. So we kind of went through the two cases so far. That was when the bottom function dominates. The other was when the neither function dominates. So this one we have one where the numerator dominates, okay? So remember the way that this works. The numerator dominates. If we look at the difference between them, 2 and 1, this actually acts and behavior wise like a linear function, right? Because 2 minus 1 is 1, so and behavior wise, since the coefficients are both positive, it will start off in the negative, right? As I go to negative infinity for my inputs, my function output goes to negative infinity. As I plug in large values for x, right, I will get out large values out. It acts overall like a linear function, but it has all kinds of other stuff going on. There's asymptotes, there's zeros, there's, other things going on. So let's go ahead and factor. So the first is x minus 3 times x plus 2 over x plus 1, right? So factoring tells us what the zeros are. So my zeros are -2 and 3, okay? And my whole is at -1. I'm sorry, not whole, but my vertical asymptote is at -1. So when I look for zeros around my asymptote, I need to plug in values in between -2 and -1, and also between -1 and 3. However, between -1 and 3, I already need to check a value of x equals 0, so I really only would have to look at one side of that, right? Now, since the degree between these two, right, the numerator and denominator is a difference of 1, I have to find the slant asymptote. I'm going to have a slant asymptote as well as a vertical asymptote, right? So I do my synthetic division, especially since I'm dividing by a linear factor. Sorry guys. So I'm going to use the 0 of that, which is -1. Start off with 0. Again, it's 1, -1, -6. So 1 plus 0 is 1. Multiply, I get a -1. Add that, I get a -2. Multiply that as a +2, and I get a -4 out. Okay. So this will help me find the equation of my slant asymptote. When I divide these, it's the same as x minus 2 minus 4 over x squared minus x minus 6. So as a standard division. The slant asymptote is this linear equation without the remainder portion. So x minus 2 is my slant asymptote. It acts just like a vertical asymptote, except it's slanted, right? So I have a slant asymptote of y equals x minus 2. I can't cross this line at all, okay? My y-intercept is what happens when I plug in 0. So -6 over 1 is a -6, okay? So let's look at my end behavior. It's a difference of 1, okay? The numerator dominates, so it acts like a linear function. When I plug in very, very negative values, I get very large negative values out. When I plug in very large values, I get out very large values, right? So it acts like a line. It acts like a polynomial of degree 1, okay? So again, note that the end behavior follows that of the slant asymptote. The slant asymptote also is a linear function, right? That has an end behavior of negative infinity, infinity, depending on which direction you're going. So let's look at the limits at the vertical asymptote. So again, I really only have to check one value in between -2 and -1, because I know as I approach x equals -1 from the right, I'm getting out negatives, right? So as I approach from the right, I'll get negative values out. Again, we'll still use these factored forms, just check values. So the value I want to check is in between -2 and -1. So -3/2, okay, or 1.5. That'll be negative. This will be positive because 2 is more than 1.5. And then this will be negative. So I'll have a negative on top, a negative on bottom. Overall, it should be positive, okay? So overall, be positive. So as I come from the left towards -1, I have positive infinity as my limit. Here, I don't actually have to check a value. I know that'll be negative because of what happens at 0. I get a negative out. So in between -1 and 3, I already know what happens. It's negatives always because there's no other zeros. So it stays negative. But if I want to check a value anyways, I have a value I checked. So it agrees, which is nice. So that's pretty much all we need, right? We can plug everything together. So this is -2, okay? This is 3. This is my y-intercept, okay? That's my vertical asymptote, and x equals -1. And that's my slant asymptote. So I have an asymptote here and an asymptote here. So I have stuff going on here, okay? I'll have stuff going on here. And it could have been possible that I had stuff going on here instead and stuff going on here instead. But since I already know points, I already know where the action is happening. It's going to happen here, and in between this blocked off area is where the other stuff is happening. Now, if I had a point here, right, instead of this, if this x-intercept was up here, I would have some stuff happening up here and then some stuff happening on this side, right? Actually, I wouldn't have anything happening on here. I'd only have stuff on top. So I'm sectioned off into 1, 2, 3, 4 pieces. So depending on where my points exist tells me what's going to happen. Okay. So this is a 0, multiplicity 1. So I know I cross at some point. I know as I get close to negative infinity from this side, I'm going to be positive. So it's going to come like this. And I know I go to, my end result is that I keep going negative. So I'm going to start to hug this line. All right. So this, again, my end behavior follows the behavior of the slant asymptote. Okay. So I'm going to hug this line. I'm going to continue to go to negative infinity as my x's go towards negative infinity. And I cross here. And as I get closer to negative 1 from the left, I continue to go to infinity. Same thing here. These are where my points are, so I really just follow this dashed line and this dashed line, and I cross through. So I go towards negative infinity, I'll cross here, and then I'll just kind of follow this line. And as x gets large, well, so does the slant asymptote, so I'm just following my asymptote. I always get close to my vertical and slant asymptotes. And that's my graph. Okay, so that's kind of the 3 cases. We didn't do more than that because for this last example, there's 4 more cases within it. But whenever the polynomial dominates on top, you just treat it like a polynomial that behaves with whatever the difference is, right? Here the difference from the numerator and denominator is a degree of 1. Its end behavior is like a polynomial of degree 1. Okay, if the difference here was 1, but there was a negative here, like this was negative x squared, well then it would act like, instead of a positive line, like a negative line. It would still act like a linear function, but with a negative multiple in front, so these would be switched, right? So that part of it is actually pretty straightforward. Again, you just have to do a couple examples to familiarize yourself with how it works. Okay, so we only have one more section in chapter 3, so I will see you guys on the last video for chapter 3.